In 1987, in the village of Bugu, Mali, a water well driller leaned over a dry borehole with a lit cigarette. The resulting explosion burned with a blue, smokeless flame that fascinated the locals and burned without pollution. It took 25 years for anyone to analyze the gas properly, but when they did, the results shattered a century of geological dogma. The well contained 98% pure hydrogen. Today, that well is not a relic. It is a power plant run by Hydroma Inc., providing carbon-free electricity to the village, proving that the Earth is not just a passive vessel for fossil fuels, but an active chemical reactor capable of manufacturing its own clean energy. This is the story of white hydrogen, also known as gold or geologic hydrogen, a resource that promises to decarbonize the world for a fraction of the cost of current renewables. For most of the 20th century, geology textbooks taught that hydrogen does not exist in its pure form in nature because it is too light, reactive, and mobile. Scientists believed that if it ever existed underground, it would have escaped into the atmosphere eons ago. This belief was so strong that when oil drillers in places like Australia and Kansas encountered massive spikes of hydrogen in the 1960s and 70s, they viewed it as a nuisance, capping the wells and walking away from what we now realize were fortunes. The reality is that the Earth generates this fuel continuously through several geological processes. The primary engine is called serpentinization. This occurs when water trickles down fissures and meets iron-rich ultramafic rocks, like olivine, at high temperatures between 200 and 350 degrees Celsius. The water oxidizes the iron in the rock, effectively rusting it, and in the divorce of molecules, pure hydrogen gas is stripped away and released. This happens on a massive scale in mid-ocean ridges and ophiolates. A second process, known as radiolysis, occurs in the ancient, stable hearts of continents called cratons. Here, radioactive elements like uranium, thorium, and potassium naturally decay, emitting radiation that splits water molecules trapped in the rock's pores, creating a slow, steady pulse of hydrogen over millions of years. We can even see the evidence of these leaks on the surface. In Brazil, Russia, and Australia, the landscape is dotted with fairy circles, subcircular depressions with bleached soil and stunted vegetation where hydrogen seeping out of the ground has consumed the soil's oxygen. These circles have become the treasure maps for modern hydrogen hunters. The hunt has now exploded into a worldwide race. In France, specifically the Lorraine mining basin, researchers from the CNRS and the University of Lorraine lowered a probe into old coal mines in 2023, hoping to find methane. Instead, at 3,000 meters deep, their models predicted hydrogen concentrations could reach 98%. This single deposit is estimated to hold between 46 and 260 million tons of hydrogen, which is staggering considering the entire world currently produces only about 90 million tons per year. Companies like La Française de l'Énergie are racing to secure permits there. In South Australia, the regulatory environment is moving even faster, leading to a frenzy of exploration by companies like Gold Hydrogen, which is re-entering wells drilled in the 1930s to confirm historical logs of high-purity gas. In the United States, the industry has moved to the boardrooms of Silicon Valley. A startup named Coloma, based in Denver, has raised over $305 million from investors like Bill Gates' Breakthrough Energy Ventures, Amazon, and United Airlines. They are using AI and satellite imagery to identify geological sweet spots in the mid-continent rift, betting that the American Midwest will become a hydrogen titan. Even in Spain, Helios Aragon is targeting a reservoir in the Pyrenees estimated to hold over 1 million tons, though they are currently fighting legal battles regarding climate laws that ban hydrocarbon exploration. The reason for this global excitement is pure economics. Currently, green hydrogen made from renewables via electrolysis costs between $3 and $8 per kilogram. Gray hydrogen made from dirty natural gas costs around $2 but comes with heavy carbon emissions. White hydrogen, however, is projected to cost as little as 50 cents to $1 per kilogram. At $1 per kilogram, hydrogen reaches economic parity with diesel and gasoline, making it cheap enough to decarbonize heavy trucking, shipping, steel manufacturing, and fertilizer production without massive subsidies. Furthermore, there is a hidden economic bonus: helium. Many white hydrogen deposits, particularly in the US and Australia, show significant concentrations of helium, a critical high-value gas used in MRI machines and semiconductors. The revenue from selling the helium co-product could cover the entire cost of drilling, effectively making the hydrogen free. However, tapping into this subterranean treasure requires overcoming an engineering nightmare. Hydrogen is the smallest molecule in the universe, making it incredibly slippery. It can leak through seals that are tight enough to hold methane, and, more dangerously, it can permeate solid steel. This causes hydrogen embrittlement, where the gas diffuses into the metal's crystal lattice, making it brittle and prone to catastrophic cracking. Standard oil-field steel tubing cannot be used. Engineers must turn to expensive high-nickel stainless steels or glass fiber reinforced composites to prevent wells from failing. Once out of the ground, the gas often needs purification, as it can be mixed with methane or nitrogen, and then transported. Since hydrogen has low energy density by volume, it must be compressed to 700 bars or liquefied at -253 degrees Celsius, both of which are energy intensive. The immediate solution is blending it into existing natural gas pipelines, but for pure hydrogen, new infrastructure is required. There is also a massive legal void. In many jurisdictions, white hydrogen does not exist in the law. In the United States, land ownership often splits surface rights from mineral rights. It is unclear if hydrogen is a mineral owned by the mineral rights holder or if it is a product of water owned by the surface rights holder. This ambiguity is a ticking time bomb for litigation. France and Australia have updated their mining codes, but places like Spain have inadvertently trapped hydrogen projects in limbo due to anti-fossil fuel legislation. Finally, we must address the environmental paradox. White hydrogen is carbon-free, but it is an indirect greenhouse gas. If it leaks into the atmosphere, it reacts with hydroxyl radicals, which are the atmosphere's detergent responsible for breaking down methane. If these radicals are busy reacting with leaked hydrogen, methane lingers longer, effectively increasing global warming. Recent studies suggest hydrogen's global warming potential is about 11 to 13 times that of CO2 over a 100-year horizon. This means a white hydrogen industry with high leakage rates could accidentally accelerate near-term warming. Additionally, stimulated hydrogen projects which inject water into hot rocks to force serpentinization raise concerns about water usage in arid regions, though proponents argue saline wastewater can be used. We are currently in the Wildcat Era of white hydrogen, comparable to the oil industry in 1859. By 2030, we expect the first commercial hubs in Australia and France. By 2050, if the technology matures, white hydrogen could provide a baseload supply of clean fuel to balance the intermittency of wind and solar, reshaping geopolitics and turning nations with the right geology into the new energy superpowers. We might spend the next century mining the very element that powers the stars, right from beneath our feet.